Use clickers right away. Hello, check. I actually combine these two topics together because they're so short. They don't look short, but they are. So we will define the magnetic field as the region of space around a magnet where another magnet will experience force. Okay, that's annoying.
I think you're eating batteries.
Not charged.
Oh.
I don't know. Can't count.
Looks like you gave me one of these.
I don't know.
Wayne, what kind of
Give it to
shenanigans
Mustafa.
are you going to do before you graduate?
Okay, so we will define the magnetic field as the region of space around a magnet where another magnet will experience force. I already kind of showed you that. We're going to define it formally. Okay, Lane, I've begun. It's now my turn. My turn. Demonstrate and diagram magnetic fields using lines of force. I will tell you that drawing magnetic field lines is almost identical to electric field lines. It's pretty darn easy. Okay, so you have experience with that already. We're going to include bar magnets, horseshoe magnets, between light poles, on light poles, and so on.
You got any horseshoe magnets?
Do I have horseshoe magnets? I do.
Can we try them all today?
Oh, like we're going to play horseshoes with them or what?
No,
Like play with them? Yeah, I'll get to playing with them, yeah.
Today?
Well, no, not today. Today's not really the day for me.
It's ruined my day.
Sorry, man. Well, after I showed you the coolest thing?
Yeah. Thanks, Mr. Man.
All right. Describe the concept of magnetic poles and demonstrate that like poles repel and unlike poles attract. You probably already know that. We'll describe magnetism using the domain theory. In other words, explain why magnets work, including ferromagnetic materials, the attraction of iron objects to north and south poles. We will investigate the influence and effects of the magnetic field of the Earth, including auroras, magnetic declination, and inclination.
Yeah.
How do they make a magnet, Mr. Man?
How do they make a magnet?
Like in factories, how do they make a magnet?
Like a horseshoe magnet?
Like any kind of magnet.
Well, there's different kinds of magnets. I actually have a magnetizer. Let me see if I can see it there.
Like what? You can turn any piece of metal?
Pretty much, yeah.
Yeah.
If you bring me some metal from the shop, I'll turn it into a magnet. Not right here.
Can I do a welding for a second? You can turn it into a magnet?
You can bring one. All it really is it's a magnetizer. I don't know. Is it magnet? Is it ferro? What is it? Like what's?
Metal.
Yeah, but is it stainless steel?
It is.
Then it won't. Stainless steel isn't magnetic. So all this really is plug it in, obviously, and there's probably like a big coil of wire in here that when you turn it on, that coil of wire becomes an electromagnet. You know, like at the junkyard, the big electromagnet that picks up the cars, right?
Yeah.
And they can turn it on and off, right?
Yeah.
So same idea. You can turn this on and off. It turns it into a magnet. When you put a hunk of metal in a magnetic field, the hunk of metal becomes magnetic.
Even if you take it out of the magnet?
Yeah, if you put it in there long enough, and if the hunk of metal is, like if you get me just raw iron,
Yeah.
very magnetic. Steel has been sort of hardened a little bit. It may not work as well. When you get, I'm jumping ahead here quite a bit. When you get lava, I don't have lava. I have lodestones. When you get a volcanic eruption, wasn't it like a volcano just recently?
Yeah, there was.
Where was that? Not that, no, I think in the last month or something.
Yeah.
I'll send this around. When you get a volcano, the lava is actually has a high iron content,
Yeah.
and because it's very soft and warm, in the Earth's magnetic field, it actually becomes magnetic. So these rocks, these are natural rocks. There's little staples in here.
So can you turn that into a magnet?
It's already a magnet.
In case to put it against something else.
It is. See, there's a little staple in it. Like it won't stick to it. Like it's not that magnetic, but it's not more like staple. But it only works when the rock is like soft and warm, and the atoms can move around. The domains can line up somehow. When I was in Greece a few years back, you notice that these rocks are can you see they're kind of rusty, kind of reddish?
Yeah.
Okay, so that's an indication that there's iron in the rock, and it's just rusting, right? So when I was in Greece, my wife and I were on this active volcano, and I saw all kinds of these rocks, and they were very rusty like this. In fact, the swim trunks that I had on were like really red after because there's so much iron in the water. And I just happened to inadvertently bring home a rock. Stuck in my shoe. And I thought, oh, this is gonna be awesome, because this will be a actual magnet. It wasn't, I was very disappointed. No, it wasn't. So the only ones I got, these ones are like, they're block lodestones.
So why wasn't it?
I don't know, that's a good question. And maybe it was, and it just wasn't. Well, no, it just wasn't that strong. Like these will actually pick up staples, but maybe it was, and it just didn't work as strong. I don't
So
know.
if you leave it in the flat thing for long enough, it'll get stronger?
Well, it would have to be turned on. But again, these magnets were formed when this rock was really young, when the rock was soft and hot like lava. Now it's stuck on the rock. So.
Oh, we turn it on. They're back. Come on.
Okay. You will notice that there's, in that first unit there, do you see any solved problems? There's none at all, right? So it's all very theory-based. Electromagnetism is a little bit more
Problematic problems. Describe and demonstrate the phenomenon of electromagnetism. I sort of showed you that already today. Diagram and describe qualitatively the magnetic field around a current carrying wire. We may get to that. Some of this stuff we may not get to. We will not perform a lab to demonstrate that B is proportional to I. I've never gotten that far.
How far?
Actually, I think I got there once. We won't get that far. But we will solve my favorite problems. F equals Bill. F equals Bill.
That's FA?
FB. B stands for magnetic, of course.
What is that little, yeah.
I think there's a typo here. I don't think that should be there. This should just be F. That should be like that. And I'm not sure what the deal is with that one. Anyways, there's your outcomes. Flip the page over. Is the next one? Oh no, the next one is this free press article. And then we'll do the little quick quiz. Yeah, send it around, you guys. The little quiz. Okay. So this is from 2004. It's a few years back. Free press. When a 6-year-old New York boy died after a metal oxygen tank flew across a hospital room toward the giant magnet at the core of the MRI scanning his brain, David Holt realized that something needed to be done. Accidents that damage equipment or cause minor injuries are not uncommon when staff forget to remove pagers from their belts or fridge magnets in their pockets. Who walks around with a fridge magnet in their pocket?
Sometimes.
Really?
Yeah.
And you think I'm a nerd?
Holt, a principal research officer with the National Research Council Winnipeg, said it took a death to galvanize the research community. He's built a prototype detector for the entrance to the MRI suite that is so sensitive it keeps the door to the scanner room firmly locked if someone walks through the detector wearing a bobby pin. And you've seen it. You guys that have had MRIs, I was just down there a couple months ago for an MRI. In Winkler, big giant door, warning, any metallic objects, like they...
Did you go off?
No, it was Tanner that was going for an ear MRI, but I had an MRI done on my head, and it's a little unnerving kind of thing, because if you've got any metal at all, right, like if you've got like a clip in your body, a pin, anything metallic in your body.
That's why you have to wear it now.
Yeah, well, no, I'm actually still not walking around naked. That's why you have to take your clothes off. Yeah, buttons, coins in your pocket, anything like that. The prototype, which took 3 years to develop, looks like the airport metal detectors passengers have to walk through, but it picks up only magnetic materials, because some metals are not magnetic, like our aluminum tube here, right? Iron, steel, and magnets can turn into fast-moving projectiles in an MRI suite, but silver, gold, copper, and brass are safe. So if you've got a gold ring, no problem. When Holt steps through the detector wearing his belt, it sounds a lot of alarm, but it raises no objections to his brass zipper. Holt is negotiating with a U.S. company that wants to manufacture the detectors while paying a licensing fee to a government-funded agency. The potential market might include hundreds of research hospitals in the United States. Holt estimates it might cost about $40,000 for a detector, but it can prevent damage to MRI machines worth millions of dollars. That's an enormous investment to have an accident with. Most patients wear only hospital gowns into the MRI suite, but they may have implants in their bodies of which they're not aware. In one case, an aneurysm clip twisted inside someone's body to align itself with the magnet, breaking a blood vessel. So in their brain, they had a little metal clip.
Yeah, they asked.
Yeah, that would be a bad thing.
They asked you to like a pacemaker.
Yeah, there's a long, it's like a 2-page list of, they ask you questions when you go in for an MRI. They do not want you in there with metal.
Like a metal plate.
Staff are the biggest safety risk because they are fully clothed and sometimes forget the rules. So if you're a worker in there, you've got to remember you can't wear well, they just wear regular clothes, right? But they know no coins in your pockets. They know what. They probably have something in a scanner like this. Like this is from 2004. I should have asked when I was down.
It's like a more in-depth
Geez, what was I doing? Holt said he didn't realize Canadian coins were magnetic when he first came to this country from the U.S. Had a new job in Ottawa. They shot out of my pocket straight into the magnet. Fortunately, no patient was in the MRI. Skip down a sentence there. Patients in Winnipeg are questioned extensively, even about their work history, since welders can have metal fragments in their skin. Holt's invention takes advantage of the low-level magnetic field near MRIs, which magnetizes metal in the area. When magnetized metal plates pass between coils in the detector, it creates a voltage that sets off the alarm, just like when I created the electric current in the tube this morning. So because that electricity is generated, it sets off the alarm.
How would you know if you don't? How would you not know if you had it in your head?
Maybe.
Oh, I just forgot.
Maybe
that.
you, well, I mean, if you've got brain surgery, and I don't know, they put some stuff in my head, and like, I know that when I had my MRI on my knee, I had a hernia when I was a kid, and I had a metal, or like a mesh sort of fabric in here, and I wasn't sure if it was metallic mesh or if it was plastic mesh, so I told them about that. I said, oh yeah, you're good. But if you forgot, like if that was something that was done 40 years ago, you're like, oh yeah, I forgot about that, right? I forgot there's a big metal spike in my head. So there you go. There's a use for magnetic field. It just holds, like a hernia is like when your guts kind of come out through your muscle wall. So they put the mesh in. The mesh is like sort of like a patch. Put a patch in.
Go grab a clicker. Well, it's not like they come out into your cavity of your body, right?
Oh my God!
Nah. So, this is the first minute. Lenny, can I have my turn now, please? This is the first where objects are attracted or repelled to each other. Pretty straightforward. Everyone got it? Yay. Should we just stop right there? 100% for everyone, right?
Holy!
Easy, like
100%. No
magnetism. Magnets have a north-seeking pole and a south-seeking pole. I'm going to ruin a childhood memory for you today. Magnets have a north-seeking pole and a south-seeking pole. That, my friends, is true. Two of the same kinds of poles repel each other. That, my friends, is true. North and north will repel. South and south will repel. Opposite poles will attract each other. Yay, everyone got it right. The area around a magnet that behaves like a magnet is a magnetic field. Yay. See, 100%. You guys know all about magnets. The further apart two magnets are from one another, the stronger the force that attract or repel them. That, my friends, is false. The further apart they are, the weaker they are. And in fact, it's just like gravitational field, just like electric field, inverse square law. Easy. Just calm. When magnets are broken into small bits, the bits themselves can become small magnets. That is true. If you take a magnet and snap it in half, both ends will become magnetic. And what was part of the North Pole will now become, will be South Pole. And I have a broken magnet I can show you.
Yeah?
Yep. Right away. Naturally occurring magnets in nature are called, I sort of gave that away when I sent the box around, they're called C lodestones, not D polar stones. Which of these is not needed to create a simple electromagnet?
A copper wire.
No. You don't need the bulb. You need a battery, you need a copper wire and a nail. If you wrap the copper wire around the nail, battery, you'll get a little magnet.
I can get copper and mail.
And I would like to show you this video, but I don't know what it was, so guess it disappeared. I apologize. I have another video I can show you. I have another one I can show you. But you can put away the clickers, yes. I want to talk to you about the Earth's magnetic field. You're probably familiar with the idea. Graham, put it away, please.
Maybe right about here.
You're probably familiar. I'll just wait. Lane, just Chill. Relax. You're probably familiar with the concept that the Earth has a magnetic field. You probably don't know what its value is. I happen to. It's 5 times 10 to the minus 5 Tesla. Yeah. If I'm ever on Jeopardy, I'll get that one right. Did you know that the Earth's magnetic field actually has changed over time?
Yeah.
Okay, so this is an article from 2004 once again. Okay, Cole, come on. You're just distracting everyone. We've all seen that. Please, please, please.
I got it apart.
Calm down. Holy moly.
I'm learning.
Down the middle of the Atlantic Ocean is what they call the Mid-Atlantic Ridge, which is why they call it the Mid-Atlantic Ridge, because it's in the middle of the Atlantic. Next time Earth's magnetic field flips, compass needles will point south instead of north. But scientists can't say when it will occur, and until now they've disagreed on how long the transitions take. A new study pins down how long it took for the last 4 reversals to play out. It also finds that the dramatic turnarounds occur more quickly near the equator than at higher latitudes closer to the poles. That means that folks living during the next reversal, which some scientists actually speculate might be underway right now, will see compasses change and behave differently in different locations, said study leader Brad Clement of Florida International University. Earth's magnetic field is thought to be generated deep inside the planet. An inner core of solid iron is surrounded by an outer core of molten iron. They rotate at different rates, and the interaction between the regions creates what scientists call a hydromagnetic dynamo. It's something like an electric motor, and it generates a magnetic field akin to a giant barmaid. So the Earth has a magnetic field because of that iron core rotating. The process is not completely understood. In fact, one study suggests the planet's mantle, which surrounds the core, also plays a role. However it works, the setup has been in place for at least 3 billion of Earth's 4.6 billion years, scientists figure. But the field is shifty, periodically growing weaker, stronger, weaker, moving around and even flipping its polarity entirely.
Why does it flip the polarity?
I'm going to tell you right away. In the past 15 million years, there have been 4 reversals every 1 million years, or about 1 shift every 250,000 years. So that explains. The last one, however, was 790,000 years ago. That might suggest that we're overdue for a big change. Not necessarily so, say Clement. The flips are not periodic. In other words, they don't adhere to a schedule of even intervals. So you can't really predict. But they do believe that we are in the middle of some sort of shift.
What will happen if the third shift?
There will be some complications. Yeah. Well, probably not the end of the world. There could be some consequences, though. Yeah.
And of course, it's 2004, so everyone expects it.
Yeah. Exactly. Yeah. The intensity of the magnetic field from the Earth has been dropping for the last 2,000 years, and it has dropped significantly during the past 2 decades, and quite likely one more since then. Clement said, one recent study shows the decline in strength amounts to 10% over the last 150 years. So is there a flip in progress? Some scientists speculate that a reversal is underway. Clement said that's like forecasting that the bottom will drop out of the stock market because it's gone down the past few days. We just don't know, he said. We're only going to be able to look back, like scientists way in the future, we'll be able to look back and say, yeah, in 2015 it was in the middle of a reversal. Researchers also have not known how long it takes for the magnetic field to make a transition. Studies have suggested anywhere from 1,000 to 28,000 years are required to initiate and complete a reversal. I'll explain how they all know this when I'm done. I'm just going to read it all and then I'll explain how they know this. It's generally accepted that during a reversal, the geomagnetic field decreases to about 10% of its full polarity value. And after the field is weakened, the directions undergo a nearly 180-degree change, and then the field strengthens in the opposite polarity direction. A major uncertainty, however, has remained regarding how long this process takes. Clement examined sediment cores gathered from deep ocean sites in a National Science Foundation program. The cores provided readings at multiple sites for the past 4 flips. He found that each one took about 7,000 years. Interestingly enough, there is a significant variation depending on the latitude. Depending on how far north you go, it changes significantly. So which way is up? It takes less time, around 5,000 years, for the reversal to occur at lower latitudes near the equator. And it takes longer, about 10,000 years, for the flip to play out near the poles. So not only would compasses gradually do a somersault in readings, but Arctic dwellers would see changes that wouldn't match what tropical observers would note across generations. So there might be some person who lives like in Ecuador, right on the equator. They see the flip, we've got an Inuit person, they say no flip, what's going on? And that could last for 1,000 years. We can have this really weird magnetic field on it. Yeah, well, nobody understands how the shift occurs. Perhaps Clement says the magnetic field shrinks to essentially nothing, leaving several mini poles at the surface before the main poles reveal on opposite sides of the world. Scientists have plenty of reasons to seek a better understanding. For one, the magnetic field lines extend out beyond Earth's atmosphere and provide the first line of defense against strong solar storms. Clement wonders how the reversals might affect navigation by migrating birds and other animals that key in on the magnetic field to find their way. So birds use this magnetic field. They know which way is south because of the magnetic field. Smart birds. They got a little compass. 7,000 years is probably enough time for them to adapt. Clement has demonstrated that magnetic field reversal events occur within certain time frames, regardless of the polarity of the reversals, says Carolyn Ruppel, Program Director of the National Science Foundation's Division of Ocean Sciences. The studies detailed in the April 8th issue of the journal Nature. Blah, 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 blah. 2004, so old news, right? How do they know all this stuff? If you look back on the front page, you'll see a couple diagrams. Okay? And the first one shows the Mid-Atlantic Ridge. Basically, there's this huge mountain range down the middle of the Atlantic Ocean. The ocean's pretty deep. Okay? And that Mid-Atlantic Ridge is actually volcanic. Okay? And so, if I could just, let me just pull this up here, make it a bit bigger. This is how they know all this stuff. Okay? So what they do is they go down to this Mid-Atlantic Ridge, and there is basically a chain of volcanoes down the middle, kind of thing. Okay? You guys know about plate tectonics?
Yeah.
Okay, so the Earth's plates, right? This plate is moving towards, this is North America over here, and this is Europe. It moves at about a rate of about 2.5 centimeters per year. Okay? So as the magma, as these volcanoes erupt underneath the ocean, they lay down fresh, soft, iron-rich rock. Because it's soft rock, like the lodestones I passed around, they align themselves in the Earth's magnetic field. So if this is north and this is south, then all of those rocks have, like if you took out a chunk of rock right there, it would be north and south, like that. Well, what they did was they go farther across, they go further out this way, and there's this white stripe. Well, instead of being north and south there, here it's north and south like that. And then this one is north and south. And then this one here, the south is up here and the north is there. So it's like there's these magnetic stripes. Can you see the stripes with the naked eye? No, you pull out the rock and they align it. They make sure they keep track of which way was pointing. But there's these magnetic stripes down the side. And why is that? Because these plates are moving like this, right? So they can figure out how long ago this stripe existed, knowing how fast that plate is moving to the left. That's how they know all this stuff. So it's pretty cool. Why is it important? Like, is the Earth's magnetic field important to us?
Yes.
What does it do? Like, why do we need it? It does good stuff. It protects us from solar radiation. Huge solar radiation. You guys probably have seen the Northern Lights recently, right? That's because of the Earth's magnetic field. Okay,